Welcome to Number Theory. Today, we are going to explore one of the most elegant and powerful concepts in mathematics, known as multiplicative functions. Imagine you are running a highly efficient recycling plant. If a truck brings in a mixed load of glass and plastic, your plant can split them onto two completely separate conveyor belts because they share no common materials. The machines work perfectly in parallel. In number theory, a multiplicative function behaves exactly like this efficient factory. It is a mathematical rule that perfectly splits apart when you feed it numbers that share no common basic ingredients. Let us dive in and see how this works. Before we look at the formula, we need to understand the two foundational ideas behind this concept. First, what is an arithmetic function? It is simply a mathematical machine that only accepts positive whole numbers, like 1, 2, or 3 as its input and spits out another number as its output. Second, we need to understand what it means for numbers to be co-prime. Two numbers are considered co-prime if their greatest common divisor is exactly 1. This means they share no common dividing numbers other than the number 1 itself. For example, 8 is only built from the prime number 2, and 9 is only built from the prime number 3. Because they share no common prime ingredients, 8 and 9 are perfectly co-prime. Now that we understand what co-prime numbers are, let us look at the mathematical rule that defines a multiplicative function. The formula states that f of m times n is exactly equal to f of m multiplied by f of n. Conceptually, this means the function's value for a combined number is just the product of the function applied to each piece individually. But there is a strict condition. The variables m and n must be co-prime. If they share common factors, like 4 and 6, which both share the factor 2, this splitting behavior would not necessarily hold true. If m increases, the combined product increases. But as long as the new m remains co-prime to n, the function will still perfectly split into two independent calculations. To make this formula more concrete, let us look at a visual representation of how this splitting works. Here you see a diagram illustrating the function applied to the number 36. Because 36 can be broken down into 4 multiplied by 9, and we know that 4 and 9 are co-prime, the function splits perfectly. The large blue circle representing f of 36 branches down into two separate independent calculations, f of 4 in the green circle and f of 9 in the orange circle. The large multiplication sign between them shows that you simply multiply their individual results together to get the final answer. This diagram teaches us that complex, combined inputs can be safely dismantled into smaller, isolated parts. Before we move on to more complex properties, let us see this formula in action with a concrete example. We want to test if a very basic operation, the squaring function, follows our multiplicative rule. We are given the function f of n equals n squared. To test this, we need to set up a scenario using two variables. We take two arbitrary positive integers, a and b, that are co-prime. We then plug their combined product, a times b, into our function. This means we must square the entire combined quantity, giving us f of a times b equals the quantity a times b squared. We have successfully set up the initial substitution. Continuing from our setup, we now apply the basic rules of algebra. When you square a product of two numbers, you can distribute that square to each number individually. This algebraic step allows us to break the expression apart into a squared times b squared. Now, we look back at our original function definition. It tells us that a squared is exactly the same as f of a, and b squared is exactly the same as f of b. By substituting the formal function notation back in, we arrive at f of a times b equals f of a multiplied by f of b. This perfectly matches our fundamental equation, proving that the squaring function is indeed multiplicative.
Physically, this means the area of a rectangle with combined side lengths scales exactly as the product of their individual squared scales.
Now that we have successfully tested a function, we can use our formula to uncover a mandatory feature of all multiplicative functions. What happens when we plug in the number 1? We are setting out to derive the value of f of 1. We start with a basic identity. Any positive integer n multiplied by 1 remains exactly itself. So n equals n times 1. Next, we apply our function to both sides of this equation. Because the number 1 shares no prime factors with any other number, n and 1 are always perfectly co-prime. This is a crucial realization because it gives us permission to use our special splitting rule on the right side of the equation. Continuing our derivation, we expand the right side by strictly following the multiplicative property, giving us f of n equals f of n multiplied by f of 1. Now, we must assume our function does not just output 0 for every single number in existence. Under this assumption, we can safely pick an integer n where the output f of n is not 0. Because it is not 0, the rules of algebra allow us to divide both sides of our equation by the value f of n. By doing this, the f of n terms cancel out, leaving us with the beautiful and simple result that f of 1 must always equal 1. This proves that every single valid multiplicative function is firmly anchored at the starting point of 1. So, we have proven that f of 1 is always 1. And we know how the function splits. This brings us to the true power of multiplicative functions, calculating values for very large numbers. To do this, we rely on prime building blocks. Every whole number can be broken down into a unique recipe of prime numbers. Remember, prime numbers are numbers that can only be divided by 1 and themselves. Because different prime numbers share no common factors, their powers are always co-prime to one another. This means if we have a massive number, we can factor it into its prime components, and our multiplicative function will neatly split apart for every single prime block. This turns an impossible calculation into a series of small, easy steps. To see how we use these prime building blocks, let us introduce a custom formula. Imagine we are given a specific rule that tells us how a function behaves when it encounters a single prime number raised to a power. The formula states that f of p to the power of k is simply equal to p plus k. Conceptually, this rule takes the prime base, p, and adds it to the exponent, k. If the prime base increases, the output increases linearly. If the power increases, the output also increases linearly. As long as we can break a large number down into pieces that look like p to the power of k, we can use this simple addition rule to solve the whole puzzle. Now that we have our custom rule for prime powers, let us apply it to a concrete example. We are asked to find the value of the function for the number 60, written as f of 60. Our first step is to break the number 60 down into its prime factorization. We find that 60 is equal to 2 squared times 3 to the first power times 5 to the first power. Because 2, 3 and 5 are distinct prime numbers, the blocks 2 squared, 3 to the first and 5 to the first are all completely co-prime to one another. We have successfully set up the prime factorization. Continuing with our calculation, we can now use the multiplicative property to split the function apart. Because the prime blocks are co-prime, f of 60 becomes f of 2 squared multiplied by f of 3 to the first multiplied by f of 5 to the first. We have broken the difficult problem into 3 bite-sized pieces. Now we apply our given rule, which is p plus k, to each individual block. For the first term, the prime is 2 and the power is 2, giving us 2 plus 2. For the second, the prime is 3 and the power is 1, giving 3 plus 1. For the third, the prime is 5 and the power is 1, giving 5 plus 1. For our final steps, we simply perform the basic addition inside each set of parentheses. This gives us the numbers 4, 4 and 6. These numbers represent the function's output for each of the isolated prime blocks. Our final step is to multiply these three separate results together. 4 times 4 is 16, and 16 times 6 gives us our ultimate answer. The final result is 96. Physically, this demonstrates that instead of needing a massive lookup table for every single number up to infinity, we only need to know how the function behaves for prime numbers. Once we know the prime behavior, we can easily build the answer for any other number in the universe. You might wonder why mathematicians care so deeply about whether a function is multiplicative. The answer comes down to computational survival in the real world. In fields like cryptography, which keeps your bank accounts and private messages secure on the internet, computers must evaluate complex functions for numbers that are hundreds of digits long. If a function is not multiplicative, calculating its value for a massive number might take a supercomputer thousands of years. However, because these functions split perfectly, a computer only needs to break the massive number down into its prime factors and calculate those much smaller pieces. This exact property is the absolute backbone of the RSA encryption algorithm, used globally today. We have covered a lot of ground today, so let us review the key takeaways. First, a multiplicative function is a special mathematical rule that respects the independence of numbers that share no common factors. When you feed it a product of co-prime numbers, it neatly splits into the product of the function applied to each number separately. Second, we proved that every valid multiplicative function is firmly anchored at f of 1 equals 1. Finally, this elegant splitting property allows us to understand the behavior of infinitely large numbers simply by understanding their fundamental prime building blocks. You now understand how mathematics breaks massive, impossible problems into small, easily solvable pieces.